have a binary search tree that works with integers, right? So let's see how that's going to work. The first thing is, what is it that we're going to need if we're going to make a binary search tree? One of the things we're going to have is nodes, right? We talked about nodes being like train cars. So what kind of thing are we going to need in terms of our nodes? Does this need to be public or private? Like, get me started here and walk me through the process of thinking what's going to have to be in our nodes.
Private static class.
Okay. Private, because nobody has any business talking about them besides us. Static, because there's no business the node has reaching up and grabbing data out of the tree here, just like in the linked list. Great, thanks, Henry. Class, and then I'm going to call it a binary int tree node. Or we could just call it node, right? Whatever, okay? What is in a node? What kind of data is going to be in a node? So somebody else, Henry got us started. What do we need in a node?
Reference to another node.
Okay, how many references to other nodes?
Specifically.
Got to have two, right? We got to have a left pointer and we got to have a right pointer. What is their data type in this world that is not generic? What's the data type of left and right?
Binary int tree node.
That is their data type, right? They are references to other things of the same class as me, right? Everything's nodes pointing to nodes, right? Nodes are linked based on the fact that they point to other nodes like them. Similar to a linked list, but now we've got two references. One points to its left child, one points to its right child. And then what else do we need here? We need some data, right? In this case, it's just going to be integers. Are these things all going to be private or public, and why?
They can be public because they're within the static class.
Because they are in a private class, right? A private inner class, we can make them public here, which makes our life a whole lot easier when we're writing the code. Okay? All those things make sense to you? Okay. How about a constructor? Might as well, while we're here, public, binary, blah, 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 right? We probably never would create a node without any data, right? It's unlikely that we would have need to create a node without data. So we probably at least need one constructor. And then in that constructor, what do we need to do? We can say this dot data equals the data that comes in. And then what are the left and right going to be set to?
Null.
We don't know any better, right? We don't know any better. So just for completeness sake, let's just set them to null so we're clear that, yep, when we create a brand new node, we don't know anything about their children yet. Okay, we probably don't know at that point. Okay. It's not like a linked list where sometimes a second constructor is helpful because you already know what goes next and you're inserting it. That's not going to happen here, right? When we create a node, we actually don't know their children pretty much any of the time. So I think this one constructor is probably all we really need for our nodes. Okay. We might want a toString, but I don't even know if we care, right? I don't know if we even care about that at this point. But if we wanted to, we could make a toString and just maybe return the nodes data as part of the toString, but we'll come back if we need that. Anybody have questions about what we set up here and why? Okay, should all make sense based on our talk yesterday. Okay, now in the tree itself, the BST, right, for integers, what is it that we need here in terms of data? We need one global variable, and what is that?
Root.
What data type is root?
Binary int tree node.
Binary int tree node, right? Root is a reference to the first node, right? Root is pointing to that very top first node at the top of the tree. And at the beginning, if we were making a constructor here, public binary search tree int, right? If we're making a constructor for that, we probably set root to null. Okay. That's all it needs. Now, maybe later we're going to make a size, right? That would make some sense that maybe we would have a size variable. So maybe we do that, right? Just so we have it at our fingertips in terms of using it later, right? But for now, maybe we also write something that goes in counts, like we did before, just for practice, right? Maybe we'll actually go and count the nodes just to prove that we can do that kind of that kinds of traversal and recursion and all that fun stuff. Okay. All right. So everybody good with the fact that this is what we need to even get started. We haven't written any useful methods yet, but we know that we need that. We can't do anything without that much. Okay. I get a read from everybody. Is everybody cool? Everybody understanding why and what we've done here? Okay. Okay, Idris, you good? Sandra, I think I saw you. Did you show me anything, Sandra? You good, or do you have questions, Torin? Okay. All right, everybody's good. All right. Okay, so now let's get into some of the fun stuff and let's figure out how to do the recursive thinking, which is going to blow our minds a little bit, right? It's going to be a little bit crazy. All right, so the first thing we need to write is we've got to have an add method, right? So let's figure out first, let's remind ourselves how we think about add, right? And let's think a little more specifically about the code. So let's add first this number 1, and let's pay attention to how the code has to think. First of all, remember that your entry point is always root, right? We're always going to start from the top. So